Hello, welcome everybody. So what I've done here today is I've gone through the conservation of energy for a differential control volume, which is one thing that was left, and there are two problems that were also requested. So I've gone ahead and solved those, and I'll also give it to you as sample problems. And okay, so with regards to the energy equation, now the energy equation is simply a conservation of energy for differential fluid volume or control volume, and it can be derived in multiple ways. You can either take a differential control volume, which is, let's say, dx, dy, dz in size, and then calculate, do the conservation, make sure that all the fluxes, etc., are written properly, and then just account for everything and get that equation. Or you can just go ahead and use the integral formulation to start with, and this is the integral formulation. Remember here, the E here is the specific total energy, and that is the specific internal energy plus the kinetic energy. Now I think in your book the E here is slightly different than what I have taken. Another difference is the book considers Q dot into the control volume as I think the Q is positive when it is out away from the control volume, whereas here we have specifically written Q dot into the control volume, and that this is just bookkeeping. You have to do it properly, that's all. So here we have the energy, the time derivative of the change of energy in the control volume plus the energy flux through the control surface, and on this side you have the heat input into the control volume, the work done on the control volume by the body forces, the work done on the control volume by the surface forces. So we just apply the same idea as before, like consider a fixed control volume so that this ddt can be taken inside, and this url is equal to u, and then you repeat basically the procedure from before, where that's q dot into cv is some flux vector dot with the n vector dA, and this is the work done on the control volume, and this can be expressed in this form. This is the work done on this control volume by surface forces, and this is obviously due to the traction vectors that are there. So you have to take into account the stress tensor here, and this is what it will be if you do that. So finally you have to change this control volume, all the control surface terms into control volume terms. So then you have to apply the proper theorem to do that, and if you once you apply that, this is what it becomes. This term thankfully is already in a control volume form. This particular steps that you take here, you have to take it for this q dot also. Okay, I have not done it here, so I've sort of skipped that. And so this basically this control surface term translates to this particular term, right? This is equivalent to this. So you convert all the control surface terms into control volume terms, and then basically bring them under the integral, and you will end up with this kind of an equation right here. And this tells you that the energy equation can be given in the integral notation. It can be written like this. Okay, so this again I said it's in the book. I'm not doing a very thorough job of deriving this, because it involves the exact same ideas that we have already used before, so I don't want to repeat myself. Okay, and now for the two sample problems that I've already solved again. So everything here, this video is going to be short because everything is sort of solved, and I'll just explain it to you. So in this question I had given this in one of the lectures, and I had said that the piston moves at a constant speed v, and the initial density and the length are rho naught and L naught, and the gas has a density rho t, so this gas density is changing with time, because this length is also changing with time. So this piston is moving inwards with a velocity v. So the question was to determine rho t. Now this is since the gas velocity u here, what has to happen is for this piston to move, the gas has to move. Now the gas here has to have a velocity of 0, right? So the gas is not in a uniform motion in the inside this cavity. So at this point it has some velocity, at this point it has 0 velocity. So you can assume that the gas velocity varies linearly from the piston surface to the boundary. So in that case, what you can do is you can say that this uxt, which is the gas velocity inside this volume, this has a this particular form, v1 minus x L by t, okay, where this is the instantaneous length, right? So once you know, but what is LT? LT is some L naught, as we had already said, assume, minus Vt. Okay, so this V, by the way, is this V. And then you apply your continuity equation, and you assume one-dimensional flow. So you have a simple continuity equation in this form. The other terms are not there, and this is now going to be this two terms equal to 0. So then you can this particular quantity you should be able to take the derivative of. And once you do that, then so this x, so because you have taken a linear assumption, this term x will sort of drop out, and you will be left with del rho del t with some quantity equal to 0. And then you can rearrange this in this particular fashion, and then you integrate both sides, right? So on this side you integrate from rho naught to some rho, and on this side you integrate from time into equal to 0 to some time equal to t. When you do that, you will end up with, you will see that the log of rho by rho naught, I have skipped some steps obviously, is equal to, yeah, so when you do this integration, this sort of comes out, this result. So this is the final answer. Okay, so let me know if the two answers don't match, and then we can talk about it, what might have gone wrong. Okay, and I did receive quite a bit of the last time we were discussing, we had some people say that do the sprinkler problem. So I just took one of those problems, which this is the classical sprinkler problem, where you have a lawn sprinkler. This is just the circle to denote that this, okay, I've made a small mistake here. This is not D, this is R, okay. And so there is, this is the top view, okay, and this is the side view. So you have flow coming in at Q and it's leaving, and let's say the pipe diameter here is some small d, okay, and so this is now going to come out, and it's coming out with a velocity v here. But in the top view, this is coming out with a velocity v such that it makes an angle theta with this normal, okay. And the rest of the parameters are given, like this, it's rotating at an angular velocity of omega, this length is L, there is a force F here, and I'll tell you what the force F is for. And the first case that we consider is, we ask ourselves, what is the force required to hold the sprinkler at 0 velocity? Okay, so hold the sprinkler steady. So if the sprinkler is steady, so if, let's say, no rotation due to F, then the problem does become rather easy, because all you have to do is you have to consider a stationary control volume that encloses the sprinkler right here all over, and then you apply the angular momentum principle to that control volume. So it's a static control volume, and you will have a time derivative term, so you can assume a steady flow and just cut this part out, and then you have this particular term, will come to that, equal to the sum of all moments. So the sum of all moments usually is broken up into two categories, one being the surface moments due to the surface forces and another being moment due to the body forces. Here the body forces, nobody is asking you to take that into account, so you can neglect that. This particular quantity works out to this. This 2 here is because there are 2 arms of the sprinkler. Okay, so I've just given them this a space so that you can see that there are 2 arms of this, and this is the flux coming out, rho v pi d square by 4. As I said, this is d. From the top view you can't make out this, I've just drawn it as a line, but there is a diameter of this pipe. So, and then k vector, sorry, so this k vector should have been here, I didn't have any much space. The moment, okay, due to the force F here is simply Fl into the k vector, and then you equate, and this is rather straightforward for you to work out, and this should be the answer. Okay, now part 2, let's say the sprinkler is rotating and it's rotating at a velocity that is known to you, so the omega is no longer 0. So this, in this particular problem, the omega is not 0. So in that case you have now a control volume again attached to the sprinkler, but now the control volume is moving, and it is not an inertial control volume obviously, so you have to consider the non-inertial version of the angular momentum equation, right? So if you have to do that, then you have obviously all the previous terms, but the new term that you have is this, right? And this term, I think I hope all of you remember where this comes from. This simply comes because of the rotation of the reference frame attached to the non-inertial control volume compared to the inertial reference frame. And let's say the inertial reference frame is capital X, Y, Z, and the non-inertial reference frame is X, Y, small x, Y, Z. So all these terms are there. Now, often, sometimes it becomes confusing as to which R and which omega, etc. that is, but here I am just making it clear as to what these terms mean. So small x, y, z means that this is in the rotating frame of reference, and this is the omega dot in the rotating frame as compared to the inertial frame, etc. So I have not repeated this this subscript for all the omegas because they are the same, so I didn't want to make it very cumbersome. But then this is the term that you have to subtract from your moment. Now this term again, as previously, it's 0, and that's straightforward. This other term right here, this is to be evaluated exactly the same way, and you'll get the same answer as this. So this is just the same term, right, as this answer right here. But here I have just written Ez, because what I've done is, because of the nature of the problem, I've written this R vector as R, ER, omega as some omega E. This is the unit vector in the Z direction, this is the unit vector in the R direction, and U is again V times ER. Right? Okay. So now when you evaluate this huge term right here, okay, you end up with, so this is an integration over the control volume, and what you do is you assume that the pipe is uniform, and if the pipe is uniform, then you just this is the area, and then you can convert this integral into a 1D integral from r equal to 0 to r equal to capital R. And this entire term if you evaluate, it reduces to this particular term right here. Okay, I've skipped quite a bit over here. So if you are getting confused, you just let me know what if you're not able to work this out. Okay, and this particular integral here, this is nothing but the moment of inertia, I. So let's assume that this I is known, and this integral is rather easy to evaluate. So you end up, this entire term ends up being this term. Okay, so now you solve just like previously, and you should end up with this particular equation right here, and this is the final answer. So give it a shot. If you are confused, we can have a discussion on this sometime. Okay, so I will end this lecture. It's going to be a short lecture because I've already written everything out for you. So okay.